In talking to non-technical people recently about learning, I've realized there's not always a good understanding of the relationship and the differences between the kind of learning current machine learning algorithms do and the kind of learning that human minds carry out. I mean, ML algorithms like neural nets, decision forests, Bayesian learners, including the ML algorithms at the core of transformer neural net architecture that runs chatbots like ChatGPT and Claude and so forth. These algorithms are genuinely learning, but there's other kinds of learning beyond what they do, which are also very important. And we can talk about continual learning, about transfer learning, about lifelong learning, which I think of as developmental learning, right? So the way most ML algorithms are doing learning, it's sort of like pattern recognition in a data set, right? So you have a bunch of knowledge and you don't know what are the patterns in this knowledge, and you don't tell the system what are the patterns in the knowledge. The system looks at your data set, your body of knowledge, and it tells you what are the recurring patterns comprising the hidden structure in that knowledge. And this this can be very hard. It can be very valuable. Now, humans do that too. That's in a way the crux of our intelligence, right? I long ago started thinking about general intelligence as the behavior of a complex self-organizing system, recognizing patterns in itself and its environment, including patterns regarding which of its actions tend to lead to which results, internally and externally, right? So clearly, recognizing, learning the sets of patterns in a body of data, this is critical to how generally intelligent minds operate, right? However, there are some key properties in how learning operates in human brains and the brains of a bunch of other animals that aren't shared by the ML algorithms that are in common use today. So one of these is continual learning, which is something we take very much for granted as human beings, right? All that means is we can keep on learning, at least until our brains get too old and we get dementia and then eventually die, right? But we learn new stuff, then eventually we will lose track of some of the old stuff that we learned a long time ago, but it's still there in a sort of attenuated form, and we can often bring it back. I learned Spanish in university. Amazingly to me now, I read 100 Years of Solitude by Gabriel Garcia Marquez in Spanish when I was in college. I choked on Don Quixote with all the obscure, archaic Spanish constructions. Now, that knowledge of Spanish is greatly attenuated in my brain now because it's been a long time since I had to deal a lot with Spanish, and I've been filling my head with a lot of other stuff. But, when I go to Mexico, I find within a few days, Spanish starts to come back, right? Now, current standard neural net systems, are used inside LLMs and so on, they're not like that. They have a problem called catastrophic forgetting. You can teach them a certain amount of stuff. Then once they sort of get full, then when they learn new stuff, they'll all of a sudden forget a huge amount of the old stuff that they used to know, right? And this is not, it's not a naturalistic way of learning, and this sort of problem is why we have big models like ChatGPT 5.4, and then we freeze that model rather than just keeping to have the model learn more and more and more and more based on every new interaction it has, right? So LLMs can do what's called in-context learning. Like you'll have a frozen model like GPT 5.4, and then to a limited extent, that frozen model can still learn something within each interaction it has with you inside the neural network. And that happens by the dynamics of activation, like energy spreading around inside the neural network. But the weights between the neurons in the neural network that comprises ChatGPT 5.4, like those weights on the links between the neurons, which are set during the training of the neural network, during the learning of the neural network, those don't change after the 5.4 model is learned and then frozen, right? And I mean, the reason for this is catastrophic forgetting and related phenomena. So this is one of the holy grails of modern neural net learning, is what's called continual learning, like the ability to just keep on learning, learn from one task, then learn to do another task, learn one context, learn to do another context, and just keep that going with some more gradual and sensible attenuation of the old knowledge, rather than just losing it all at once, right? I mean, you could imagine if a neural net could continually learn, it would keep learning. When it got full, it might start forgetting the old stuff. Like then maybe you add new neurons and links onto it, so it has room for the new stuff and the old stuff, right? I mean, it makes sense, but that's not how current systems work. And this ties in with something called transfer learning, which is the ability to learn stuff in one domain and then transfer it to a different domain. And it may seem that LLMs are not bad at that, because in their interaction with you, I mean, you could be talking about, how people act in China, and the LLM could transfer something it learned about how people act in Russia to help understand how people act in China. But the thing is, this is all based on what the LLM learned from reading the whole web, which has stuff about Russia and China and all these other countries in it, right? So the thing that LLMs and other standard neural net models say are not good at doing is taking a leap out of distribution, right? Meaning something that bears very little resemblance to anything in their training data set. So, I mean, an example would be if you trained a neural net only to predict financial time series, and then tried to get it to predict weather time series instead. Can it, figure out which of the lessons from finance are portable to weather and which ones are not? Like, this would be a big leap of transfer learning, and people are reasonably good at this. I mean, little kids are doing transfer learning all the time because they're always being thrown into new situations, different than the ones that we're prepared for. And I mean, as it happens in modern society, we're always being thrown into new situations different than the ones our brains evolved for as well, right? Because our brains evolved for life in the Stone Age. So these are two different problems: continual learning and transfer learning. You could imagine ways to solve one of them without solving both of them. On the other hand, it seems like the brain accomplishes both of these things in a kind of coupled way, right? And it seems like the key to solving both of these is, in part, knowledge representation. It's how how is the knowledge that's learned represented inside the mind, the knowledge base of the AI system, right? And if the knowledge is represented in a cleanly organized way, where different sorts of knowledge are sort of stored in different parts of the system, either physically different parts or different parts that are dynamically coordinated together into separate networks in the system's behavior. If the knowledge is kind of decomposed in a modular way inside the AI's knowledge network, and if you have abstraction, so rather than just storing a lot of special cases of all the detailed things the system has seen, if you're also storing some more general purpose abstractions, and these more general purpose abstractions are also modularized and are appropriately linked in some way in the system's dynamics to the modules storing different sorts of particular knowledge. If you have this right sort of abstraction and modularization in the knowledge representation inside the AI system, then I believe you can get both continual learning and transfer learning kind of in one fell swoop, right? Now, this is very abstract. One thing you can observe is that logic systems, which are not neural nets at all, but they try to do learning by abstract logical reasoning using probabilistic and fuzzy logic and predicate logic and so on. Logic systems naturally lend themselves to abstraction and modularization. However, so far, applying logic systems to huge amounts of perceptual data, like what comes into a camera eye, or even all the text on the web, it's been challenging. Logic systems haven't scaled up to the level that neural nets and some other sub-symbolic systems have. I mean, I think with Hyperon, we are going quite far toward scaling up logic systems in ways that hasn't been done before. And we're doing lots of cool experiments with large-scale PLN, probabilistic logic network inference, on Hyperon atom space knowledge graphs stored in the Mork knowledge repository and so on. But still, even though I think we can scale up logic quite a lot using Hyperon, I do think dealing with, say, sensory data or robot arm movement data, huge financial data sets, dealing with a lot of this data is still going to be easier using neural or other sub-symbolic methods. So then you get in the direction of neural symbolic systems, using symbolic reasoning systems for the things they're good at, using neural net systems for the things that they're good at. But then you have the question, can you get this modularized and partially abstracted knowledge representation to work well within neural net systems? And here's where I think shifting from the back propagation learning algorithm that's standardly used in commercial nets today toward different learning algorithms like predictive coding, or a novel variant of predictive coding I've come up with called causal coding. Shifting to predictive and causal coding, I believe, can allow this modularity and abstraction of knowledge representation to arise within neural networks. Now, predictive and causal coding aren't the only way. Like Ken Stanley, a long-time genetic algorithm researcher, he published a cool paper Might have just been last year. Things go so fast. It seems like 1,000 years ago. Ken Stanley published a cool paper called Fractured Entangled Representations, and he showed that evolving a neural net by some of his genetic algorithm methods leads to internal representations that are much more nicely modularized than what happens with backpropagation. The thing is that neural net evolution algorithm of his, well, super cool, doesn't scale up very well. And with predictive and causal coding, we're trying to get modularity and abstraction in the internal representations to drive scalable learning, right? Which obviously is super important. That's one of the big lessons we've seen from the recent successes of backpropagation trained neural nets like LLMs. Like one of the big lessons we've seen is, scale is very important. Now with smarter algorithms, hyper and predictive coding, we may need less data than the current backpropagation methods need to get more intelligence, but you're still going to need a lot of data, right? You may need less processors to get a certain amount of intelligence done, but you're still going to need quite a lot of processors. So I think this is a challenge we can solve soon, possibly the next couple months, definitely in the next year or two, getting both neural nets and logic systems at scale with different strengths and weaknesses regarding different kinds of data and different problems. I mean, getting these to do continual learning and transfer learning effectively by adopting architectures that will learn the right kinds of representations. And there is some creativity needed here, right? So I've been playing with these alternate neural net architectures where you model cortical columns and do predictive and causal coding based learning within each column, and then you train another neural net to combine the outputs of the columns to give an output. And the kind of physical division of the neural net into columns helps with modularization of knowledge, even if not in the most simplistic way. Like, much knowledge still exists across sets of different columns. And this leads on to another aspect of learning I wanted to go into, which is what's been called in the AI field lifelong learning, which I think of more so as developmental learning. So continual learning, transfer learning, can be studied in academia in fairly limited ways. Like, can you train a model on task A and have it transfer knowledge to task B? Or can the system, learn to recognize 500 classes of images without forgetting too badly the early classes when it gets to the later classes, right? Whereas what humans do involves continual learning and transfer learning wrapped up in a much broader enterprise of, causing a human organism to keep doing its thing, keep feeding itself, beating off its enemies, mating and reproducing, hopefully enjoying itself a bit over the course of its life, right? And so this leads to what you can think of as lifelong learning. But the way I think about lifelong learning, it's not just continual learning over a really long time. And it's not just transfer learning across a whole bunch of different contexts. But a lot of what we do in our lives is develop, right? Like, the version of me Ben Goertzel at age 2 was very different than the version at age 59 who's rambling at you right now, right? I mean, I remember my first memory at age, I think I was just barely 2, watching Neil Armstrong walk on the moon. I mean, it's weird. My first clear memory is watching TV, because I hate TV. But, I mean, that was a big thing. Like, every adult was there, eyes glued at the screen, right? And I remember he said something weird like a small step for man, a great leap for mankind. I was confused. I thought that mankind was like a midget man, right? So it was a small step for a guy, but a big leap for that little tiny mankind. And I think I was 4 or 5 when I finally realized mankind was some kind of silly abstraction, rather than they brought a tiny little man on the spacecraft. And that 2-year-old who was thinking these silly things about man and mankind, right? I mean, he had a lot in common with the 59-year-old me. Like, I was reading all day, starting age 2 or 2.5 or something, right? And I was interested in space and going where no man has gone before. But I mean, I can't even tell you honestly how much real commonality there is between me and my 2-year-old self, right? I can see more clearly incredible differences between me and myself in my late teens at age 20 or 25, right? I mean, it's not just that I may have become a little wiser or better at regulating my emotions, or that I no longer have like a recurrent loop of thoughts going all the time that's out of my control. I'm more in touch with just the joy of existing at every moment. I'm much more able to now and then stop rambling and listen to other people and try to fully enter into their way of being. I mean, I've been through all sorts of fascinating mind states of, seeing the whole world from the top down rather than my eyes, perceiving time going forwards and backwards. And I've hopefully integrated a little bit of humility along with my long-standing overweening ambition, right? Loads of changes I've gone through during my life. Now, day by day, there's only a few days when I feel like, whoa, I've had a transformative experience. I'm very, very different than the previous day, right? On the other hand, over time, it's not just that I've learned more and been able to transfer knowledge from, the situations I had in college to the situation I had when I started my first company, right? Or transfer knowledge from when I raised my first batch of 3 kids in my 20s and 30s to raising the 2 little kids I have now. It's not just that I've avoided catastrophic forgetting and have transferred knowledge from old situations to new situations, right? I mean, I have changed my own self in a fundamental way. I've changed my methods of representing knowledge. I've changed the processes that I use to learn and reason, right? And this is development. And one thing that surprised me as I've gotten older, and I'm fucking almost 60 now, unbelievably. One thing that surprised me as I've grown older is this doesn't stop, right? Like, I've evolved in my own thinking and feeling and being and understanding of self and others quite a lot in the last 10 years, just like I did in the first 10 years of my life. Like, you keep on developing, and current neural nets utterly don't do that, right? So of course the series of GPT models has developed, and we've all seen it from GPT 3.5, which was the first transformer that really made me think, okay, now we see some significant elements of how and why the singularity is near. And 3.5 to 4, 4.501, 5, 5.2, 5.4. There's been development, but the development has not been the same network reorganizing and improving itself, right? And the development has been human beings taking what they learned from the previous networks and then designing and building a new network. And what we do over the course of our lives is like, we start out as Ben Goertzel 1.0, and then based on interaction with the outside world, we transmogrify ourselves into Ben Goertzel 2.0, Ben Goertzel 3.0, and so forth, right? And this developmental learning, I think it requires the same modularization and abstraction of knowledge as what you need to get continual and transfer learning, but it also requires probably some other elements, right? I mean, it requires some meta reflection aspect. It requires the system to be continually learning and transfer learning about its own self and its relation with its environment, right? So you could do a lot without developing, of course, but I think in practice, the way we're going to get to a human level AGI and then a super intelligence is going to be heavily walking up a hill here. It's going to be heavily developmental, right? Because if you can make a system that can develop itself, you only have to be smart enough to figure out the initial condition and the developmental approach, right? If you build a system that can't develop itself, then you've got to figure out the entire learning, reasoning, meta-representational approach for the, final adult level AGI mind that you're building. And I think while it's not easy to figure out developmental learning methods, it's going to be the most tractable way to do things. So yeah, that's 3 aspects of learning: continual learning, transfer learning, and lifelong developmental learning. And these are all building on, the basic ability to recognize patterns in data sets, which machine learning algorithms are so good at doing now. But what's happened is the methods that we have optimized for doing more basic forms of learning, just recognizing patterns in big data sets, the methods we've optimized for these have been optimized so hard to efficiently learn patterns in big data sets they've been optimized so hard for that they're not able to do continual transfer or lifelong developmental learning, right? So what we need to do now, we need to introduce a new generation of learning algorithms that can learn in some ways more like people. And I think everyone in the field knows this, but one issue is that it may require taking a modest step backwards in an algorithm's ability just to recognize maximum number of patterns in a data set, right? Because if you're optimizing just to recognize all the patterns in the data set and you're throwing out all the mechanisms that would let you do continual transfer or lifelong learning, I mean, you may do very well at what you're optimizing for. And if you built a system that's representing things in a more flexible way, so it can do continual transfer and lifelong learning, I mean, this more flexible system, it might need some getting up to speed time before it could do as well as its more narrow-focused competitors at just crunching patterns and data sets. And that's what we're wrestling with now in the AGI R&D team in SingularityNet and the Hyperon project. Right? I think we're taking paradigms like probabilistic logic reasoning and predictive and causal coding learning in neural networks, and we're trying to get them to scale up to the level that they can, not only outperform backpropagation neural nets and other standard ML tools at finding patterns in big data sets, but can also display these other important properties of natural systems learning, right? And so the next part of this story is what are the specifics of the methods that we in SingularityNet / Hyperon / ASI Alliance are using to address these problems, right? And that gets into how does predictive coding, how does causal coding work, how does probabilistic logic networks inference work. There's a framework called Transweave I've introduced that gives a general way of structuring transfer learning that holds across neural nets, evolutionary algorithms, inference systems. And I posted something online about Transweave last fall. I'm going to put together a short paper on that to submit to the AGI conference. It's coming up in San Francisco in July. But this video is long enough by now, so I'm going to leave it here. But hopefully I've framed what some of the challenges are, right? And as a side point, a bit into the nitty gritty, but just to show how this tension between ML and AGI raises its head in practice. We've been discussing on our internal SingularityNet messaging board what are good benchmarks for measuring progress on continual learning. And I mean, what you find is most of the standard benchmark tests used to analyze continual learning can be hacked in the sense that you can make systems that are not AGI-capable at all, but are good at doing continual learning, task on task in that very specific way. So I've laid out, a battery of different continual learning tests, including some involving, continual and transfer learning among qualitatively different tasks in Minecraft, in different sorts of simulated indoor environments, in a robot simulation world. And I mean, you can design ways of measuring continual and transfer learning that are more robust and that will help you get toward AGI systems. But it's interesting. Yeah, look at that deer. That deer is trying to transfer learning about other humans to me and figure out how scary I am, which it will soon decide is pretty scary, I think. Yeah, you can design tests that help you advance your algorithms toward AGI, but if you look at the tests for continual and transfer learning that are commonly used in the academic field, I mean, these can be and routinely are, whether intentionally or not, gamed by researchers who are just trying to do well on continual or transfer learning in this very specific way, right? So, I mean, in a way, you're going from the mainstream AI industry focusing on narrow intelligence to trying to focus on general intelligence, but in overly narrowly defined ways that don't really work much toward general intelligence, like doing continual learning on recognizing images in series of little pictures or something, which, of course, getting continual learning working for learning a long series of little pictures is important, but it can be done by methods that don't work for, developmental, lifelong, continual, and transfer learning. And on the whole, I'm frustrated by the inability of the mainstream AI world to focus on these more, humanistic and transhumanistic aspects of learning. On the other hand, it's also good because it means those of us doing things in the decentralized and democratic vein have a chance of winning the AGI race in spite of having a bunch less money than big tech, right? Because at least we're focused on the right kinds of learning. We're trying to solve the right problems.